we're going to go through some examples and all of the topics that will help us with Module 1 and all of the homework questions. So let's get started. The first topic of this week is domain. And basically what domain is saying is what values can x be? So if we have this function f of x equals x over the square root of x minus 5, just what values can we have for x? And graphing it is one way that we could figure out what the x values can be, but it's not always easy to see explicitly what they can be. So one thing that we think about when I see a function like this is I have a square root, and what can't we have under square roots? Well, we can't have negative numbers under square roots, not in the real number system. So I know that what's underneath the square root has to be greater than or equal to 0. So let me go ahead and start writing. So I know underneath the square root, the x minus 5 has to be greater than or equal to 0. Is there anything else that's happening here that we have? Well, I also have a fraction, which means what can't I have in the bottom of a fraction? I can't have a 0 in the denominator of a fraction. So the x minus 5 in this case also can't be 0. And again, that's only because the square root's in the denominator of a fraction. So really what we have if we combine these two is that x minus 5 has to be strictly greater than 0. And again, that's just because under a square root we can have 0 typically, but because the square root's in the denominator of a fraction, we can't have 0. So that means that x has to be greater than 5. And another way that we write this is called interval notation. And interval notation is just giving the interval of values that x can be. And it helps sometimes to draw a number line. So if here is 0, here's 5. X can be everything greater than 5, but not equal to in this case. So everything after 5, and how we denote that we can't include 5 is we denote it with a parenthesis. So sometimes you'll see it with a parenthesis written there. It just means we can't include 5. So the interval notation would be 5 up to infinity. And infinity also gets a parenthesis. Infinity always gets a parenthesis because it's not a numerical value, so it can't technically be included. So this represents the domain of x over the square root of x minus 5. Are there any questions? Just let me know. And if we were to include 5, again, if we just had the function, sorry, I just wanted to mention this quickly. If we just had the function where the square root of x minus 5 wasn't in the denominator, then we could have that a 0 under the square root. So what we would have in this case would be that x minus 5 has to be greater than or equal to 0. That's saying positive numbers, but it could be 0, which means x has to be greater than or equal to 5. And in this case, again, just this specific case, we would include the 5. So how we would write it is we would put a bracket that includes the value of 5 up to infinity. And again, infinity always gets a parenthesis. And again, the only reason we didn't include 5 in the last case, or in our original example, was because that square root was in the denominator of a fraction, and we can't have 0 there. Does that make sense? Okay, so let's move on to another one. Okay, so we have x minus 1, and then in the denominator we have 4 minus the square root of x squared minus 9. So x minus 1 in the numerator, x could be anything. But in the denominator, x can't be anything for a couple of reasons. First, we can't have 0. So I have a few situations. I have that 4 minus the square root of x squared minus 9, that can't equal 0. And that's because it's in the denominator of a fraction. We can never have 0 in the denominator of a fraction. So if I were to add that square root x squared minus 9 over to the right, I would have 4 cannot equal the square root of x squared minus 9. So I've just added this over to the right side. And then how I would get rid of the square root is I would square both sides. And basically, I'm just solving this equation, which it's a not equal to, it's okay. I'm just solving it for x. So I have 16 cannot equal x squared minus 9. And if I add the 9 over to the left, that'll cancel it out on the right, which is what I did in the first step to move that square root x squared minus 9 over. So I have 25 cannot equal x squared. So what can x not be? The idea is I'm going to take the square root of both sides. And when I do that, when I take the square root of a number, I always get a positive and a negative value. So I get that x cannot be 5 and it cannot be negative 5. So that's one part of our domain. So I'm going to put a circle around this because we will come back to that in a minute. The other situation that we have is we still have a square root. And I still can't have negative numbers under a square root. So I still have to take into account that part. So that means x squared minus 9 can be greater than or equal to 0. And in this case, even though I have this in the denominator of a fraction, it's not the only term, so it can be 0, because if it was, we'd have 4 minus 0 in the denominator, and that's okay. We just can't have only a 0 in the denominator. So when I add the 9 over, I have x squared is greater than or equal to 9. And what happens when I take the square root of both sides is a little bit different than before. What ends up happening is I get that the absolute value of x has to be greater than or equal to 3. Because basically what this is saying is x squared has to be greater than or equal to 9. So if I plug in negative 3, for example, that would be greater than or equal to 9 once I square it. So how it changes when I take the square root of both sides is I have an absolute value of x. And what an absolute value of x means in this case is that the distance from 0, and I'll draw this in a number line in just a minute, from 0 is greater than or equal to 3. So on a number line, what the absolute value means is here's 0, and absolute value represents the distance from 0. So the distance from 0 is greater than or equal to 3. So let me draw 3, and also the negative 3. Because absolute value, when I take the absolute value of negative 3, I get 3. So all of the numbers greater than or equal to 3 would work. And I use the bracket because we're including the 3. And all of the numbers less than or equal to negative 3 would work, because that means the distance from 0 is more than or equal to 3. So putting this together with what we have with the 5 and the negative 5, let me clear a little bit of room. I thought I had an extra page that I don't. Just 1 second, sorry. Okay, so we have, let me just redraw the number line that we have. Here's 0, here's negative 3, and here's 3. Combining that with what we found earlier, that we can't have 5, I'm going to put an x over 5, and we can't have negative 5. Because remember, that's when the denominator would equal 0. But we can have everything else. So what we're going to have is a lot of different intervals. We're going to have the original interval starting from the left over, from negative infinity up to negative 5. Are we going to include negative 5? No, because if we did, then that would mean that we'd have 0 in the denominator. So our first part of the domain is from negative infinity up to -5, and we don't include the negative infinity ever, and we also don't include the -5. And then the second interval is there between -5 and -3. And how we combine these is we use this, looks like a capital U, kind of. It's the union, it means or. So from -5 up to -3, and we don't include the -5. Remember, x can't be 5 or -5, so we don't include it, but we do include the -3 because it can be -3. And then we have the other interval from 3 up to 5. So right there, from 3 up to 5. So I have another union, and I include 3, but I don't include 5. Again, that's from the first part of our domain earlier. And then the last part of our union is 5 and beyond. So, and we don't include 5, so I have 5 up to infinity. And again, infinity doesn't get a bracket ever. So this is a pretty complex domain. It's about as complex as they can get. But we end up with the 4 different parts. It can be any value from -3 and less, not including -5, and any value from 3 and up, not including 5. So I just have to, how I get rid of the -5 is by breaking this into 4 different intervals. And that's the same way I get rid of the 5. Okay, so let's move on. Okay, so piecewise functions. It looks like the graph did not stay there from earlier, so let me just redraw the graph. So this is an example of a piecewise function, and it just means that it's defined in pieces, separate pieces. They don't have to necessarily not be continuous, so it could be that the 2 parts of the curve are actually connected, but they don't have to be. They're just defined in pieces. So I want us to find the equation of the function in the graph below. And this is, again, piecewise function, so it's defined in different parts. So basically what we have is we have 2 different functions. We have this one, and we have that one. So we need to find the equation that models each one of those separately, and then we'll combine it into one function for the piecewise equation. So what we have is 2 linear functions. So looking at the first one, the open circle and the closed circle, what that means is that the graph is just not defined when we have an open circle. When we have a closed circle, it's saying that the graph is defined, and I'll explain in just a minute how that translates into the equation. But what we can do is we have a linear function. So let's find 2 points on this line, and we can get the equation of the line. So in the first case, 2 points. We could use, even though there's an open circle at the point 0, 2, we can still use that point because when we define our piecewise function later, it will get excluded. But we could use the point 0, 2 and the point 2, 0. And again, you could also use the point 1, 1. And the reason I'm getting 2 points here is because I need to find the equation of the line. And to get the equation of the line, I need a point and I need a slope. So I have to find the slope of this line. And the slope is usually denoted with the letter m. And the slope represents the change in y over the change in x. So you might see it as y2 minus y1 over x2 minus x1, where x1, x2, x1, y1 is a point and x2, y2 is another point. And it doesn't matter which point you decide is x1 and point 1 and point 2. It doesn't matter as long as everything lines up, meaning If you start with y2 in the numerator, you need to start with x2 in the denominator. So let's say that this is 0.1 and this is 0.2. So then our slope is 0 minus 2. If I use y2 minus y1, again, it's okay if you do it in the opposite order, over 2 minus 0. So I have negative 2 over 2, which is negative 1. So that means that the slope of the first part of our piecewise function is negative 1, which makes sense looking at the slope. It is a negatively sloped line, so we should have a negative value. And there's a bunch of different ways to write the equation of the line. In this case, we technically have the y-intercept again, even though it's not defined at that point. When we finish our piecewise function, we'll make sure to include that it's not defined there. But if it was, we could use y equals mx plus b. So m is the slope that we just found, and b is the y-intercept. And in this case, our y-intercept is 2. So we would have y equals negative 1 x plus 2. And typically you wouldn't put the negative 1 out in front. You would write it as negative x plus 2, and I will do that in just a minute. So our equation 1 is y equals negative x plus 2. And this is where the fact that it's not defined at x equals 0, and it is defined at x equals 2. So we want to include the interval that it's defined on. So it's between 0, less than x, less than or equal to 2. And I didn't put 0 less than or equal to x because we have an open circle right here, which means that it's not defined at x equals 0. The equation is still correct. It's just that we have to make sure we don't include 0 right there because it's not defined there. If that was a closed circle or a filled in circle, that's when we would have 0 less than or equal to x. So let's go to the next piecewise function, so the next part. So we'll just call this 2. So again, we have a line, so we need 2 points, because once we have 2 points, we can get the equation, or the slope, and then we can get the equation of the line. So what are 2 points here? And again, we can use the open circle and the closed circle when we're finding the equation. Where we exclude them is right there. So we can use the point 2, 1. That's this point right here, and the point 6, 0. So let me go to the next page. So I'm just labeling this as the second part of our piecewise function. So our points that we have are the points 2, 1 and 6, 0. And just to go back to the graph, there's the point 2, 1, and here's the point 6, 0. So I just picked 2 points on that line. And you don't have to pick those 2, it's just those 2 are the easiest to work with. So again, we're going to use this to find the slope. And the slope is the change in y over the change in x. And I just want to show you again, it doesn't matter which order you do this in. So for example, if I did this as y1 minus y2, that's okay as long as I do it divided by x1 minus x2. In the last one, we did y2 minus y1. It does not matter as long as everything lines up. So we would have 1 minus 0 over 2 minus 6. And again, that's if I'm calling this point 1 and this point 2. So then I have 1 over negative 4, which is just negative 1/4. So that's our slope. What's the difference between this point and the last, or excuse me, this line and the last one? The last one we had a y-intercept, or what it would be if the graph was defined there. In this case, we don't necessarily know what the y-intercept is. I could try to extend the line and see, but it's not very clear. So having the y-intercept is a special case. In this case, we don't have the y-intercept. So when we don't know the y-intercept, we can use the point slope equation of a line. So you could see it this way, y minus y naught equals m times x minus x naught. You could also see it, again, it just, every textbook is a little bit different. You might also see it written this way. The only difference is it's just a notation. All that this is this is the x value of the point and this is the y value of the point. So x naught, y naught is just the point on the line. Okay. So we have 2 points in this case. Is there one that we can use and we can't use the other? No, they're both points on the line. So we can use either one of them to get our equation of the line. I typically would prefer to work with a point that has a 0 in it rather than the 2, 1 point, but it's going to work out exactly the same way regardless. So I'm going to choose to use the 6, 0 point. And again, it doesn't actually matter. So the y value is 0, so I have y minus 0 equals m, which is negative 1/4, we just found that. And then x minus x naught, so x minus, and our point for x is 6. And then y minus 0 is just y, so we'll just write this as y equals, and typically the format of these equations is in mx plus b, so I can distribute this negative 1/4 all the way through. So I would have negative 1/4 x, and then the negative negative becomes positive 6/4, which we could simplify down to 3/2, and I'll do that in the next step. So we have y equals negative 1/4 x plus 3/2. And this is where the piecewise part comes in and where the open and closed circle. Where is this defined? So let's go back and look at the graph. Well, on this line here, and again, we're just looking at this line, we have an open circle on the left side, so at x equals 2, and we have a closed circle on the right side at x equals 6. So it's defined between 2 and 6. But 2 is not included because at 2 we have an open circle. And typically how we would write our piecewise function, and you might see it as y equals, it might be written as f of x equals. Those are the same notation, they represent the same thing. And we just basically put these two equations together. So the first equation that we found earlier was negative x plus 2. And the integral that that was on was 0 is less than x, less than or equal to 2. And then the second line, the one that we just found, was negative 1/4 x plus 3/2. And it was on 2 less than x, less than or equal to 6. So this function, or this equation, represents the graph in the last page. So we have 2 lines, so we can find the equations, or we can find the equations of those lines by finding 2 points on the lines. And even though we use the points where the line wasn't defined, that comes in right here. We can still use those points to find how that line was generated. Okay. So let's move on. So composition of functions. Composition of functions basically says when I have multiple functions and I'm plugging one function into another function. So if, for example, we're given f of x equals x minus 3, g of x is the 5th root of x, and h of x is x to the 3rd. What composition would result in the following? So again, composition just means plug one function into another function. So looking at the first one, we have y equals the fifth root of x minus 3. How would we have gotten that? Well, I have the fifth root of x, that's g of x, and then I'm subtracting 3 from it. So I notice that there's an x minus 3, and then there's a fifth root of x. So it looks like I am plugging g of x into f of x to me. So I am plugging g of x into f of x. I'm taking the fifth root of x and I'm replacing this x by fifth root of x, and then I have the minus 3. So I'm plugging g of x into f of x. How we would write that in composition notation is it would be written as f composed, so open circle represents composed, of g of x. It's saying plug g of x into f of x. They're almost read backwards, so sometimes you might see it without the parentheses around the f composed of g. You might see it just written like this. So if I plug g of x, which is the fifth root of x, into f of x, so I'm replacing x by the fifth root of x, I would have the fifth root of x minus 3. That would give me the fifth root of x minus 3. So looking at the next one, I have the fifth root and the x minus 3, the whole thing is under the fifth root. So again, I feel like I'm working with f of x and g of x because I have the x minus 3 and I have the fifth root. So how would I get the fifth root of x minus 3? It looks like I would take x minus 3 and plug it in for x. So I would be plugging f of x into g of x. So by plugging f of x into g of x, that's how I would get the fifth root of x minus 3. And again, the notation would be g composed of f of x. So take f of x and plug it into g of x. So take a minute and think about what you would do to get y equals x minus 3 to the third. How would you get that? Very good. Great, so we have x minus 3, and that's going to the third power. So we're going to plug f of x. So x minus 3 is going to get plugged in for h, or plugged into h. I'm going to plug f of x into h of x. So how I would write this is h composed of f of x. So it's saying h composed of f, meaning f was plugged into h. Okay, so let's actually calculate some composition of functions. So in the last case, we were given, here's the end result. How did we get here? In this case, I'm giving us two functions, and I want us to find the composition. So we have f of x is x plus 5 under a square root, and g of x is 6 over x. So first, f composed of g. of x. That's actually saying plug g of x into f of x. So another way that helps to write this is to write this as f of g of x. So it's saying take g of x and plug it into f. It's another notation for the same thing. And one benefit of writing it this way is, what's g of x? It's 6 over x, right? So I can write it as f of 6 over x. So if going up here for just a minute, if I asked you to find f of 3, what am I telling you to do? I'm telling you to plug in 3 for x. So we would have the square root of 3 plus 5, or the square root of 8. Again, that's not what we're asked, but I just wanted to mention what it actually means to say f of 3. So what does it mean to say f of 6 over x? It just means replace x by 6 over x. So I have the square root. I'm replacing x by 6 over x plus 5. So I plug g of x into f of x. So in the last examples, we were given the end result. Now we're finding the composition. Okay, so g composed of f. What is this telling us to do? It's telling us to plug f of x into g of x. So another way to write it is g of f of x. It's saying plug f of x into g of x. And we know what f of x is. It's the square root of x plus 5. So I have g of the square root of x plus 5. So we're going to take the square root of x plus 5 and plug it into g of x for x. So we get 6 over the square root of x plus 5. And that is g composed of f of x. So I plugged the function f of x into the g of x function. All right, so let's move on. So this week there's quite a few topics. So we're going to try to cover all of the possible topics that we have this week. So trigonometric functions is one of our topics. So sine theta. When we're working with a right triangle, sine theta is the opposite over the hypotenuse. So opposite the angle, opposite from the angle. And hypotenuse on a right triangle is always the longest side, or the side that is opposite of the right angle. And the adjacent side is the side that is right next to the angle theta. Theta just represents an angle. We could also have sine x, for example. So we have sine is opposite over hypotenuse, cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. You can always have this in your notes, and you can always reference it if you need to. So let's do a few examples with trigonometric functions. So let's say that we have sine x is 5 over 13. I want us to use this to find cosine x and tangent x. So when I'm dealing with sine, cosine, and tangent, that means I'm dealing with a right triangle. So let me draw a right triangle. And I can label x, or in the last example it was theta, again theta and x can be interchanged. I can label x in any of the other two corners. It's not the right angle. So I could label x here, or I could label it in the other corner. It's just all of that changes is where the opposite and the adjacent are, but it all works out the same way. So if we label x here, and we know sine x is 5 over 13. So that means we know sine is opposite over hypotenuse. So that's just basically telling us what the values are. Opposite of x is 5, and the hypotenuse is 13. Again, the hypotenuse is always going to be the longest side. Oh, that's okay, no worries, welcome. Okay, so we've got opposite of x is 5, and the hypotenuse is 13. And I knew that because they told us that sine x, and sine x, again, is opposite over hypotenuse. And like I said, please have this in your notes to refer to it whenever you need. So we need to find cosine x and tangent x. I know cosine x is adjacent over hypotenuse, which means I need that side. I need to find the value of that side. How can I do that? Well, the Pythagorean theorem. So the Pythagorean theorem says a squared plus b squared equals c squared. So that's just saying a squared, so the side, one of the legs of the triangle, plus the other leg equals c squared. The only thing, it doesn't matter which side you choose as a and b. The only one that really matters is c. C always represents the hypotenuse. So I could say that this is A, or I could call that side B. It doesn't matter. Again, the only one that matters is that the hypotenuse is C. So I called A for adjacent, so I'll just leave that as A. So I have A squared plus 5 squared, that's the other leg, equals 13 squared. And then I'm just going to use that to solve for A. So I have A squared equals 13 squared, which is 169. And 5 squared is 25, and I subtracted over, so right here I just moved over the 5 squared to the other side. So a squared is 144, and I don't need a squared, I need a, so I'm going to take the square root. And typically when we take a square root, we apply a plus or minus, but we're talking about the length of one of the sides of the triangle, so we don't need to include the negative. So we can just think of that as a length, so it's only a positive value. So I get that a is 12. So I can use that to find the cosine x. I actually also need that to find tangent x, because tangent x I know is opposite over adjacent. So I have all three sides. So I can combine this and get the values that I'm looking for. So what's cosine x? So it's adjacent, which is 12, over hypotenuse, which is 13. So this equals cosine x. Great. What about tangent x? What do we get? Very good. So tangent x is opposite over adjacent, so I have 5 over 12. Okay, I don't know why the box that I put around tangent x just moved, but it did. So let me, oh, there we go. And now it disappeared. There we go. Okay, so let's go to a few more identities. And again, I don't want you to get overwhelmed when you have these identities because you can always have them with you. You can always have them written down somewhere. So I'll give you a minute to write these down. So trigonometric identities can be really useful when we're trying to find exact values of trig values. So we'll do a couple of examples. It's also really important when we're working with finding derivatives and finding integration, which we'll learn over the course. And if you're going on to Calculus 2, you'll continue to use these. So in some cases, it's just easier to work with, say, this side of the equal sign rather than the cosine squared. Again, it just depends on what you're trying to do, but it's possible that it's easier to work with the identity. So let's look at an example. Find the value of sine of 5 pi over 12. So 5 pi over 12. The idea here is I need to actually, let's change this to 7 pi over 12. 7 pi over 12 would be better for this case. You can do this with 5 pi over 12. I think 7 pi over 12 is better. Okay, in this case. Okay, so 7 pi over 12. I don't offhand know the value for sine of 7 pi over 12. So I could try to rewrite this in terms of special angles and special angles on the unit circle. And if you're not familiar with the unit circle, you haven't thought about the unit circle in a long time, I actually have a video that I created that I can post in the course so that you can have access to it. It's about a 15-minute video, goes through all the values of the unit circle and how to find them. So I will happily do that if it's needed, or if anybody wants me to, I'm happy to do that. So the special values on a unit circle, I know the values for pi over 3, pi over 4, pi over 6, pi over 2, pi, and the list really goes on, but 3 pi over 2, 2 pi, there's many different values and in all of the different quadrants. But if I can write this in a way that uses one of these special values, I know the sign of pi over 3, for example, and I know the sign of pi over 4, or pi over 6, or pi over 2. So if I can try to write this as differently, so 7 pi over 12, this is a value I don't know the special angle value for. So if I can try to write this in another way, so I want to try to break this into the sum of two fractions, and there is many different ways that you can do this. And again, 5 pi over 12 is the same thing. You can always rewrite it in many different ways. So how could I get a denominator of 12? Well, if I break this into two fractions, and I'm thinking 4 and 3, and the reason I'm thinking that's because the common denominator of that fraction would be 12, and I'm using these, I could have also used 6 and 2, because that would have also given me a common denominator of 12. Again, it's completely up to you. The reason I thought about 4 and 3 is because 4 and 3 represent 7. So I don't know what A and B are, but how could I simplify this? Well, if I cross multiplied, I'd have 3A plus 4B that needs to equal 7 pi, because that would get me the numerator. What values of a and b do I end up with? Well, what if it was this? Well, 3 pi plus 4 pi equals 7 pi. So that means that I could write 7 pi over 12 as pi over 4 plus pi over 3. Good. So 1, and then we have to have the pi, so that's how we would get 3 plus 4, and then the pi would give us the 7 pi. So I could write 7 pi over 12 as pi over 4 plus pi over 3, because again, if I cross multiplied the two, I'd have 3 pi plus 4 pi, and then in the denominator I'd multiply, so I'd have 3 times 4, which gives me 7 pi over 12. And again, there's many, many different ways that you could rewrite 7 pi over 12. This is just one that works also. So why I would do this is sine of 7 pi over 12, I can now write as the sine of pi over 4 plus pi over 3. Which, going back to our last page for a minute, I can use this identity where I have sine a plus b, so a in our case would be pi over 4 and b would be pi over 3. And if you wrote it in reverse order, it still works out the same way. So I have sine a cosine b. So I have sine a, which is pi over 4, cosine b, so cosine pi over 3. That's the first part of the identity, just going back again to show you. And then I have cosine a plus sine b, so plus cosine pi over 4 times the sine of pi over 3. And again, these are special values from the unit circle that we know exact values for. And how we know them is they come from the right triangle. And again, I will post a video on the unit circle that I created that will help with these if you haven't thought about them a while or haven't seen them. So the sine of pi over 4 is the square root of 2 over 2. And then the cosine of pi over 3 is 1/2. So I'm just multiplying those two together. And then the cosine of pi over 4 is also square root of 2 over 2. And the sine of pi over 3 is the square root of 3 over 2. And there's really not too much I could do to simplify more. I could combine. In the first term, I could multiply the two fractions and get the square root of 2 over 4 plus the square root of 6 over 4. Other than combining those to the same fraction, there's really no reason to simplify it more. So you could leave it right there. And again, I know I've already said this, but I will post that video for the unit circle special values as soon as we are done tonight. So let's go to another example. So let's find the value of cosine squared of pi over 8. So again, pi over 8 is not one of the special values that we have on the unit circle, but we can use different identities to find the value here. So one thing that I noticed right away is it's cosine squared. So that makes me think of the identity that cosine squared x is 1/2 times 1 plus cosine 2x. And again, I got that from right here. And sine squared x is almost the same. The only difference is that this is just a minus rather than an addition. So maybe this will help. So let me rewrite. So we have cosine squared x. So in our case, cosine squared pi over 8. So on the right, that becomes 1/2 times 1 plus cosine of 2 times pi over 8. So I just replace x by pi over 8. And what happens here is the 2 cancels with the 8 and makes that a 4 when I simplify. So 2 pi over 8. So when I rewrite again, I have 1/2, 1 plus cosine pi over 4. And again, the benefit of this is I know the value for cosine of pi over 4. It's the square root of 2 over 2. I don't know the cosine of pi over 8. I would have to use what we just did in the last example and try to break it apart and rewrite it in another way as the sum or difference of two values. But I didn't have to in this case because it ended up, when I used the identity, becoming the cosine of pi over 4, which I do know the value for. So I have 1/2 times 1 plus the square root of 2 over 2. And again, you could distribute the 1/2 if you wanted to, but there's really no reason to. This is the exact value. And over the course of the term, we will work with these trigonometric identities quite a bit, so we'll revisit them as we move. So inverse functions. Inverse functions, we're going to talk about exactly how to find them, but in order to be an inverse function, or in order for a function to have an inverse, it has to pass the horizontal line test. So what the horizontal line test means is easiest to see this if I draw a graph. So let's say that I have this graph. The horizontal line test means, is there any place on this graph that I can draw a horizontal line and cross the graph more than once? Is there any place where that happens? So if I draw the graph, good. No, there isn't. If I draw a horizontal line there, I only cross the graph once. If I draw a horizontal line here, I only cross the graph once. And that's going to happen everywhere. If I draw a horizontal line, no matter where I draw a horizontal line, there's nowhere that I'm going to cross the graph twice. And what that means is that this is one-to-one, which means that it has an inverse. We'll talk in just a minute about how to find the inverse. Correct, yes. So parabola would be an example of not one-to-one. Or just good, yes. So either of these would be cases where the horizontal line test, it doesn't pass the horizontal line test. So if I draw a horizontal line, I am going to cross this graph twice, which means it does not pass the horizontal line test. And the same thing happens here. And it doesn't mean that it's possible for me to draw a line that doesn't. So for example, if I drew my horizontal line right here, it only crosses once. The question is there any place where that's not true? So for example, right here, there is no way that I can not cross this graph, in this case 3 times. So if there's anywhere on the graph at all where I draw a horizontal line and I end up crossing the graph more than once, it's not 1-to-1, which means it does not have an inverse. So, how to find the inverse of a function? I have this example, but I think I would rather do this one first. I think this one's a little easier, and we should probably start with the easier one. So to find the inverse of a function, so we have f of x equals 4x to the 7 minus 6. If I ask you to find the inverse, we can safely assume that it has an inverse. So find the inverse of the function. What we're going to do, there's a few steps. The first step is I am going to switch the x and the f of x. So I'm going to have x equals 4 f inverse of x to the 7. Actually, I'm thinking one step ahead. Hold on. There we go. Sorry, I was on the next step. So we have x equals 4 f of x to the 7 minus 6. So I switched the x and the f of x. The next step is now to change the f of x to an f inverse. And you can do steps 1 and 2 at the same time if you would like, which is what I just did. So basically, once we make that switch, we can change f of x into f inverse of x. So f inverse is represented by this notation where it's got the little -1 that looks similar to an exponent, but it actually represents the inverse. So I'm going to have x equals 4 f inverse of x to the 7 minus 6. And like I said, you could have done steps 1 and 2 at the same time. It's completely fine. And then the last thing I'm going to do is I'm going to solve for f inverse of x. Basically, that means I'm going to get everything on the other side of the equation, get f inverse of x by itself. So the first thing I want to do is I want to add over the 6. I need to move this 6 over to the other side, so I'm going to have x plus 6 equals 4 f inverse of x to the 7. What's the next step in getting f inverse of x by itself? Good. Divide out the 4. I divide out the 4 on both sides. So I have x plus 6 over 4 equals f inverse x, and that's to the 7th power. So to get rid of the 7th power, it's kind of the same idea as getting rid of a square root. We would take the square root of both sides. So what would we do here? Good. Take the 7th root of both sides. So how I would write that is the 7th root. So square roots, we don't typically write the 2, but the 7th root, we would put a little 7 out in front. X plus 6 over 4. And that represents the inverse function. Okay, so the idea, and again, I know I've said this already, I repeat myself quite a bit, you will learn. I switch x and f of x, and when I make that switch, I can go ahead and change f of x to the inverse, and then I solve the equation for f inverse of x. So I solve it the same way I would solve for an x or a y, for example. So now let's go to the last example. Again, sorry, I wanted to just do this one first because it's a little bit easier. So it is to find the inverse of f of x equals 4 over x squared plus 5. And we were given this information that x is greater than or equal to 0. So just to point out really quickly why that's given is, and this isn't necessarily something that you would have to do, I just wanted to show you why that information is given. The graph of 4 over x squared plus 5, just to give you an idea, looks very roughly like this. Well, in this form, do we have a problem? Well, if we include the left side of the y-axis, or when x is less than 0, there's an issue. And the issue is that it doesn't pass the horizontal line test. So the x greater than or equal to 0 is basically only including this side. So let me erase. No. Okay. So basically what we're trying to find is the inverse of just that part. And again, that's because the left side, if we included that, we wouldn't have an inverse. So the process is still the same. We're going to switch x and f of x. And when we do that, that makes the f of x become an f inverse of x. So I have x equals 4 over f inverse of x squared plus 5. And if you wanted to write out step 1 as just switch the two, and then step 2 where you change f of x to f inverse, that's completely fine. You're just welcome to do it in one step. And then I need to solve this for f inverse of x, which is a little bit more difficult than the last one. There's a bunch of different ways that you can do this. To show full work, what I'm going to do is I'm going to multiply both sides by f inverse of x squared plus 5. You could also move the 4. That's completely fine too. It works out the same way. So if I multiply f inverse of x squared plus 5 on both sides, I can do that as long as I do the same thing to both sides of the equal sign. What happens over on the right? Good, exactly, those two cancel out. So on the left, we have f inverse of x squared plus 5. And then all of that is times x, and all that we have left over on the right is 4. And I do want to mention there are many different ways to do this. I'm just trying to show the way that is maybe the easiest. Good, and then the next thing I need to do, again, I'm trying to get f inverse of x by itself. So I'm going to divide over the x. So if I divide out an x on both sides, so I have f inverse of x squared plus 5 equals 4 over x. And then I can subtract over the 5. Very good. Subtract the 5 over to the right and almost have f inverse of x by itself. What's the last step? Good. Take the square root of both sides. So one thing I want to mention is typically when we apply a square root, we would apply a plus or minus. But why we don't in this case, and this is what I wanted to mention with the graph, is just wanting to redraw the graph. Very rough sketch. What it means to find the inverse. So we've been finding them, but we haven't really talked about what it means. It basically means that I'm going to take this function and rotate it over the line y equals x. So the line y equals x is that line right there. So if I take this graph and rotate it over the line y equals x, I roughly have that. So that's what it means to have an inverse, is to be able to rotate the function around the line y equals x. And in this case, because we are only looking at the positive x values, we only end up with positive y values, which means we don't have a plus or minus when we apply the square root. We only have the above the x-axis. So that's our final answer. Yes, it is. So it's a combination of, the reason it really says x got to be greater than or equal to 0 is because the original graph, if we didn't have that, was this graph up here. And that graph doesn't pass the horizontal line test, because if I draw a horizontal line right there, it crosses 2. Good. So we only take the right side, and that ensures that it does have an inverse. And how that affects the answer is that we only have the positive values for f inverse of x. So yep, you're exactly right. Okay. Let's go on to the next one. Oh, we already did the next one. Let's go on to the one after. That's great. I'm glad. So again, like I said, I know this week there's a lot of topics. It's kind of going through all of the past topics for classes that would help to just kind of remind us of things that we may have seen a long time ago or may not at all. So logarithmic functions. Log functions have a very special set of properties. They don't work the way that regular functions work, meaning if I have 5 times x plus 2, this is what I mean by a function that doesn't have a log or a natural log. I can distribute the 5 and I would get 5x plus 10. It doesn't work the same way with log functions. So again, they have special properties, and that's what we're working with here. And we'll do lots of examples, but properties of logs or natural logs is if I have the natural log of a times b, so we'll see a few examples, but let's say 4 times x or something like that. The way that the natural log, you can think of it as distributes through, is it's the natural log of a plus the natural log of b, rather than the natural log of a times the natural log of b, which is what we would just feel like it would do. But natural logs, when I distribute through a times b, I get natural log a plus natural log b. Similarly, if I have natural log of a divided by the natural log of b, when I distribute, if it helps, when I distribute the natural log, how it changes is it's natural log of a minus the natural log of b. And last, if I have the natural log of a to some exponent, what I can do is I can take that exponent to the front, which is why it ends up there. So these rules are helpful for solving equations And again, as we move through the course, we'll actually find ourselves using log rules fairly often. So let's do a couple examples. I want us to express the natural log of 1 over 9 in terms of natural log of 2 and or natural log of 3. So the first step, I have natural log of 1 over 9. How can I rewrite that? Well, I have something divided by something else, so I can break it up as the natural log of 1 minus the natural log of 9, because 9's being divided. And one thing is the natural log of 1. If you go to your calculator and type it in, the natural log of 1 is 0. And again, you can always check that in your calculator. So that's gone. So we don't have to worry about that because we're trying to get our answers just in terms of natural log of 2 and or natural log of 3. Natural log of 9. How can I write this in a way that would involve a 3? Yes, so you can. Actually, hold on one second. So natural log 3 to the negative 2. Oh, I see what you're saying. The negative 2 is on the inside of the parentheses. Yes, yes, you can. The only thing is that that would end up, yes, you can write it that way. It ends up being the same thing. Okay, so we have natural log, or negative natural log, and we could write this 9 as 3 squared. Very good. Yep, and that's exactly what you would get if you wrote it as natural log 3 to the negative 2. You would have gotten the same. So then I have the exponent, so the 2 can be moved out to the front. So if we look back, that is this rule. I can take the exponent and move it to the front. So I'd have negative 2 natural log of 3. And so I don't end up with a natural log of 2, but that's okay. We didn't need one. All right. So using log rules, again, that was a pretty basic example so that we can use them to solve equations that look like this. So if we wanted to solve this equation for y, we have the natural log of y plus 3 minus the natural log of 5 equals the natural log of x plus x. So the issue here is it would be a little bit easier to solve if this x over here had a natural log with it, which it doesn't. So the easiest thing to do is to move all of the natural log terms to one side of the equal sign. So we could move the natural log x over to the left. So we'd have natural log y plus 3. And I do want to mention we can't actually break apart natural log of y plus 3 because remember the only way we can break it apart is if what's in those parentheses is being multiplied or divided. So natural log of y plus 3 we can't break into the natural log of y plus the natural log of 3. It doesn't work. So then I have minus natural log of 5 and then minus the natural log of x. So I just subtracted that over and I left the x over on the right side. And that's because it doesn't have a natural log. So if I move it over to the left, I can't use log rules because it doesn't have a log. So over here, kind of going in the opposite of what we just did. We just broke apart a natural log. Now I want to put it back together. So I can think of it as kind of factoring a natural log out to the front using the log rule. So I'd have natural log y plus 3. Since y plus 3 is positive, it would go in the numerator, because if we go back to the log rules, if I have natural log of a over b, I have natural log a minus natural log b. So anything that's being subtracted goes in the denominator. So what is in the denominator here? Well, the natural log of 5 is being subtracted, and so is the natural log of x. Good. So 5x. Both of those would end up in the denominator, and that equals x. So going back again to solving log functions, if I need to get rid of the natural log, so now I've got it down into one term. To get rid of the natural log, so I need to get rid of it because I need to get y by itself. And so I need to get the plus 3 and the 5x, those need to move. But first I need to get rid of the natural log. And how we do that is we move the base. The base of natural log is e. We don't typically write it there because when it's a natural log function, it's assumed to be e. So what this means is I move this over here. So once I move that, so over on the right, what I mean by move it is this becomes the base over here and x becomes the exponent. And now that I've moved that, all I'm left with on the left is y plus 3 over 5x. So to get rid of the natural log, I would move the base. So one thing to note, every once in a while you'll see a log function that's written this way. Log and natural log have the same properties. The only difference is log is in base 10. It doesn't have to be, but its standard log is in base 10. So if I wanted to get rid of the log, it's the same idea. I move the base, so I would have x equals 10 to the 2. So how to get rid of the log function or the natural log function is to move the base. So that's why I moved e to the other side, and it becomes the base over here, and the x that was there becomes the exponent. And now it's just a matter of solving the equation for y. So if I multiply 5x on both sides, I have y plus 3 equals 5x e to the x. You don't have to write it in this order. I just usually put e to the x at the end. And what's the last step? Good. Subtract over the 3. So I have y equals 5x e to the x minus 3. So that's how I was going to get y by itself, is I was going to combine all of the log terms into one term, and then to get rid of the natural log, I move the base to the other side, and that's what gets rid of the natural log. And then I can solve for y that way, because the only way to get y out of the natural log is to get rid of it, and I can't separate it in any other way other than to get them to one term and then move the base. All right, and I think this is the last topic tonight. So the equation of a tangent line. We're going to talk about the equation of a tangent line quite a bit throughout this course. Basically what it means, let's say I have some function like this parabola, and I want to be at this point right here. What the tangent line represents is this line right there. It's the line that's tangent to the graph at a specific point. So if we were over here at this other point, this would represent the tangent line. Or at any given point, the line that's tangent to the curve. And we will talk, again, quite a bit about this, but for right now, the equation of the tangent line. So it's still the equation of a line, point slope equation, that's where we will start, which is what we did earlier. We have this point, x naught, y naught, and then the slope. How we find the slope is a little bit different now because we don't necessarily have 2 points on this line. We are only given the point on the curve, and this is how we'll find the slope. So the limit as h approaches 0. We'll talk about that in just a minute, what exactly that means. And limits, again, are something that we'll also work with quite a bit in the coming weeks. So let's go to an example. This is the easiest way to make sense of this limit. So I want us to find the equation of the tangent line of the function x squared minus 8 at the point 2, 4. So the slope, I'm just going to rewrite what we had on the last page. The limit as h approaches 0, f of x plus h minus f of x all over h. And unfortunately, we can't just plug in h equals 0 right now because then we would have 0 over 0. And remember, we can't have 0 in the denominator. So what is f of x plus h? What does that mean? It kind of goes back to what I said earlier in the webinar. What is f of 3? F of 3 is saying plug in 3 for x. So f of x plus h is saying plug in x plus h for x. So we would have x plus h squared minus 8. So that's this part of the slope. And we do need to simplify as much as we can because we want things to start canceling out. So I recommend writing x plus h times x plus h. Just writing it out that way. That way you don't accidentally forget about the middle terms and square the first in the end. So we would have x squared plus xh plus xh plus h squared. So I just multiplied this out, so x gets multiplied by both of those, and then h also gets multiplied by both of those. You might have heard that called the FOIL method. Front terms, outer terms, inner terms, last terms. So I have x squared plus 2xh, just combined these two because I have 2 of them, plus h squared minus 8. That represents that first part of our equation. And then f of x is just the function that we're given. So we have the slope is the limit as h approaches 0. F of x plus h we just found is x squared plus 2xh plus h squared minus 8. We just found that. And then minus f of x, so minus our original function. And I put parentheses around it because I'm subtracting that whole function off, which means that negative needs to get distributed to both. All of this minus h. Excuse me, not minus h, divided by h. So what I'm going to do, distribute this negative. So I'll go ahead and do that. So I have minus x squared and then plus 8 because the negative became a positive 8. And what you'll notice is things are going to start canceling. So the x squared and the minus x squared cancel. And then the minus 8 and the 8 cancel. So the original function, this minus f of x, it will always cancel every single time. So if something doesn't cancel from that minus f of x term, it just, something went wrong. So just make sure that you distributed the negative. So we have the limit as h approaches 0 of 2xh plus h squared over h. And the problem again is if I just plug in h equals 0, which the limit is saying as h approaches 0. So one approach to limits, and again, we'll learn more about this in the future, but that's basically saying plug in h equals 0. If I do that right now, I get 0 over 0, which I can't do. But what can I do in the numerator? Well, each term has an h, so I can factor one out. And now what? Very good. This h cancels with that h, and that's how we're going to get rid of that h in the denominator. So we have the limit as h approaches 0 of 2x plus h. And again, the h that was in the numerator that factored out canceled with the h in the denominator. So now what happens as h approaches 0? What do we have left? Well, it just means plugging in 0 for h, so I'm just left with 2x. And this is the slope, but we want a numerical value for a slope. We don't want 2x. So what do? Do we know the value for x? Good. We were given that the point is 2, 4, so x equals 2. So sometimes you might see this notation, just saying we haven't plugged in 2, but add x equals 2. So our slope equals 4. So it's a lot of work to get to the slope, but that's how we have to do it, at least for right now, to get the slope of the tangent line. We still need the equation of the tangent line. We've got the point, we've got the slope, so we can find the equation. I'm going to erase a little bit because I don't have an extra page. All right, so we have our slope, it's 4, and we know the equation of a line is y minus y naught equals m, slope we just found, x minus x naught. So we have y minus 4 equals 4 times x minus 2. And typically, it's not required, but typically what you would be asked to do is to get this as a y equals, or y equals mx plus b. So if I have y minus 4, and I could distribute the 4, so I get 4x minus 8. When I distribute that 4 all the way through, and I can add this 4 over to the right side. So I get y equals 4x minus 4.